Hello, welcome to Electrical Circuits, part number 16. We'll be discussing resistive inductive or RL series circuit analysis. As you see in the schematic here, we have a series circuit. If we start off from our power source, we have one path all the way through the resistor, one path. We continue with one path through the inductor, one path full circle back to our AC power source. You see we have a 60 hertz frequency. Our resistance at the resistor is 20 ohms. We have a total of 120 volts for our circuit. We have 25 ohms of inductive reactance at the inductor. So we're going to start off looking for our impedance. We're going to use the Pythagorean theorem, C squared is equal to A squared plus B squared. We're going to change that up a little bit so we can do it in one calculation. So Z, our impedance, is equal to the square root of R squared plus our inductive reactance squared. So R squared would be 20 squared and X of L squared would be 25 squared. So when we plug those in, we come up with a total circuit impedance of 32.12 ohms. Now we're going to find our inductance for the circuit. We have one inductor, so we only have to worry about it. So our formula we'll use is L is equal to our inductive reactance divided by 2 times pi times the frequency of 60 hertz. Our inductive reactance is 25 ohms. So when we plug those in, we get 663.15 millihenries. Now, remember close counts in electricity, so we could call this 663 millihenries, or we call it 660 millihenries. That would really be close enough because we're just looking, are we in the ballpark? Yeah, if we're in the ballpark, go look somewhere else. If we're not in the ballpark, we need to look a little closer at that circuit because we do have an issue. So now we're going to find our total currents. So our total current is going to be basic Ohm's law. I sub t is equal to V sub t. We're going to replace our R with Z, so I sub t is equal to V sub t divided by Z, our impedance. So our total voltage of 120 volts divided by our impedance of 32.12 ohms will give us 3.74 amps. Now, if you notice, remember in a series circuit, the current remains constant through all components in the circuit. So we can say I sub t is equal to I sub r is equal to I sub l is equal to that same 3.74 amps. So we can populate I sub r and I sub l with that 3.74 amps. Now we're going to be looking for our voltage drops. Our voltage drop at a resistor will get a little specific. It is Ohm's law. So our voltage at the resistor is equal to the current at the resistor times our resistance of the resistor. So we know we have a current of 3.74 times a resistance of 20, which will give us 74.8 volt drop at our resistor. At our inductor, the voltage at the inductor is going to be equal to the current at the inductor times our inductive reactance. And so our current still is 3.74 amps times our inductive reactance of 25 ohms will give us 93.5 volt drop at our inductor. Now we're going to look at our VARs, our wattless power. So VARs sub L is equal to I sub L times V sub L. If you notice, that's our power formula, pi, the iron pi that we talked about in one of the first series. And so our VARs sub L is going to be equal to the current of 3.74 amps times the voltage at our inductor of 93.5 volts, giving us 349.69 VARs. Again, we could probably call that just 350 VARs. That would be in our ballpark, and that'd be close enough. Now we're going to look for our power, or our true power, which using the pi formula, P is equal to I times V, so our true power is measured on only the purely resistive part of the circuit. So P is equal to I sub R times V sub R. And so we have I sub R at 3.7 amps. The voltage drop at the resistor was 74.8 volts. So that'll give us 279.75 watts. Now remember, our true power in AC is the only one that is measured in watts. And the rest have a different name to it. And this, for our what replaces our total power in DC, we'll call our VA, volts ampere, or our apparent power, is going to be equal to our current total times our voltage total. Just straight up on power formula, the pi wheel. And so our 3.74 times 120 gives us 448.8 volts ampere. And now all we have left to do is our power factor and our angle theta. The angle theta again is our phase angle, the phase shift that our voltage is out of phase with the current. And so our power factor is a ratio of the true power to the apparent power. So it's our power factor is equal to power divided by the apparent power. In this case, it'll be the 279.75 watts divided by our apparent power, 448.8 volts ampere, giving us 62.33%. Again, we could call this 62% because in electricity we're worried about the degrees, but we really don't need to worry about the minutes and seconds because we have so many variables in our electrical circuits, heat being the number one killer. And then our last calculation to make will be our angle theta, which is equal to the arc cosine, and we plug in our power factor. So the angle theta is equal to cosine to the -1 with the power factor, and we do put it back into standard decimal notation and not as a percentage, so that would be 0.6233, giving us 51.44 degrees, or we could call that 51 degrees. Now we have our list of all of our calculated values. We're ready to go out to this circuit and make live readings with our meters and compare them to what we calculated to see if they're close. If they're close, look somewhere else. If not, dig a little bit further into that circuit. There is an issue there. This concludes part number 16 of our tutorial series. Thank you.